Hey guys, how's it going? Welcome to day 48. Today we're going to be looking at evaluating definite integrals. So we've done several things here with integrals. First thing we did is we talked about integrals as area under the curve. So we talked about that. We solved some definite integrals where we could calculate the areas. The second thing we did is we approximated definite integrals with either left Riemann sums, right Riemann sums, midpoint Riemann sums, or trapezoidal Riemann sums. Then we worked on solving indefinite integrals. Now we're going to be evaluating definite integrals. So we'll be solving them for curved functions, and these are going to be now exact answers. So evaluating definite integrals is going to start with the fundamental theorem of calculus. It's actually part 2 of the fundamental theorem of calculus, but I like to look at it before we look at part 1. So here's what it is. Okay, so it's going to start off with letting a function be, we're going to really need to tell the difference between lowercase f and capital F. Okay? Instead of using f and f prime like we use with derivatives, oftentimes with integrals we use lowercase f for our function and capital F to symbolize the antiderivative. So it's going to say this, let capital F be so let f be any antiderivative of f. And when we say any, we know from indefinite integrals that there are every antiderivative we do, there's infinitely many of them. That's why we do the plus c. But we can let capital F be any antiderivative. To make this easy, we're going to choose the antiderivative with our plus c equaling, our c equaling 0. Okay. So once we have that, here's what we know. So if we are doing the definite integral from a to b, again, we always read that from the bottom letter to the top letter, or bottom number to the top number. So the integral from a to b of f of x dx always equals that antiderivative evaluated at b minus that antiderivative evaluated at a. So we're still finding antiderivatives, so this should be a nice smooth transition from our indefinite integrals that we were working on. The nice thing about definite integrals, right, you can always check your answers on the calculator. We'll be doing that today in this video. When we solve an example, we'll be checking it to make sure it's correct on our calculator. Okay, so let's get to the example. Okay. So if you see a problem like this, we can solve this antiderivative by hand. Now, if we think about the graph of this thing, 3x squared looks something like this. Okay, we're going to be able to find the area from 0 to 3. If you remember, there was a homework where they had a curved function. I asked you to estimate that area. Okay, now we can find the exact area of that shape. It's not a triangle, right? Because that third side is curved. So we can find that exact area by solving using the fundamental theorem of calculus. So the first thing I have to do is come up with an antiderivative of 3x squared. Well, we know how to do antiderivatives, right? It's a polynomial, so we just bump and divide. And now I don't have to worry about the plus c, because I'm just going to, it says I can use any antiderivative. So I'm always just going to use plus c to be plus 0. So I can just keep it that way. Let's talk about notation here. Once we're ready to perform our definite integral, right, and we actually do the bump and divide or perform the antiderivative, we're going to switch from our s, right, integral sign to brackets. So what I want to do first is I want to perform the antiderivative and put my answer in brackets. It's just the common notation that we use. Well, the bump and divide here is very simple. I'm going to bump the power up to 3. And take my coefficient and divide by 3. So that's 3 divided by 3 is 1. Again, I don't have to put plus c because I can use any antiderivative I want. And I'm going to use the antiderivative that's x cubed. Right? I could have used x cubed plus 1 or x cubed plus 2. But I just want to use x cubed, the simplest one. Okay? I still want to remember that I'm evaluating this definite integral from 0 to 3. Okay? So we write the 0 out here and the 3 up here. Okay? So again, in terms of our notation, this function is like f, and this function is capital F, which is our antiderivative. Okay? And what I'm supposed to do now is capital F of b minus capital F of a. So I want to evaluate my top function at a value of 3, and then I want to subtract that capital F evaluated at 0. So here's what I do. I'm going to have the top number, right, evaluated minus the bottom number evaluated. So I've got 3 cubed minus 0 cubed. Right? This is because if capital F of x is x cubed, then capital F of 3 would be 3 cubed. Capital F of 0 would be 0 cubed. So basically, I'm plugging in this number, and I'm going to subtract this number plugged in. And when I do that, I get 3 cubed is 27, and 0 cubed is 0, so I get 27 minus 0, which equals 27. Okay, which is the answer to my problem. That's the exact area, right? That's the exact area here. Now, to confirm this, let's take a look at our calculator. I'm going to show you 2 different ways that we can do this. Okay. One way we can do it is by looking through the graph. So I can go to y equals, and I can graph this function, 3x squared. Now, to see this on the window, I'm going to let my x min, I'll let it be -5. I'll let my y max, x max be 5. And I'll let my y min, well, let's think about when I plug in 3 squared is 9, 9 plus 3 is 27. So I'll let my y min go from -10 to 30, just so I can get a good picture here. Okay, so this is what my graph looks like. And again, I'm finding the area between 0 and 3. So this area right here. And again, I can do that through the graph. I think I've showed you this before, but just as a reminder, we can hit second trace. And number 7 down here is our integral. So I want to integrate from 0 to 3. And notice the answer, it gives you the answer right here of 27. So that's a way you can check to make sure your work is correct. Okay. The other way we can do this is through the main screen on our calculator. If I hit math number 9, notice how down here it says function integrate. If I hit math 9, I can just type in exactly what I saw. Integral 0 to 3. My function was 3x squared. And then I say dx. Again, it tells me, confirms my answer is correct of 27. Now, obviously, these types of questions are not going to be on the calculator section because everybody can do really well as long as you can type it into your calculator. And so we have to know how to do them by hand because it will be on the no calculator section. We also want to know what exactly is going on as well. Okay, let's try. Let me just show you one thing here. I said you could do any antiderivative. So I could have done like x cubed plus 2 as a derivative. Right, then I would have had 3 cubed plus 2 minus 0 cubed plus 2. 3 cubed is 27. 27 plus 2 is 29. Minus 0 cubed plus 2 is 2. And notice I still come out with an answer of 27. I just made it harder on myself than I needed to. So it's going to always make sense to have our C value be plus 0, right? Because what's happening is that plus 2 is being added at the beginning but always subtracted away at the end. Okay? So just keep that as x cubed. Okay? So you do the integral from 2 to 4 of x squared plus 3 dx. Okay? So when I look at this, some things that are different, I'm going from 2 to 4 instead of 0 to 3. Also, notice my function here is a binomial that I'm doing the antiderivative of. You're going to want to be careful evaluating these by hand. Anytime we have a bi, tri, or any polynomial in there, just because you got to be really careful with your parentheses. I'll show you what I mean by that. The first thing I want to do is come up with an antiderivative here. Okay? So the first thing I want to do, I'm going to throw a bracket out here. So for my antiderivative of x squared, I'm going to bump and divide. And now again, with constants, sometimes people are like, oh yeah, it just goes away. No, that's with derivatives. With antiderivatives, the antiderivative of 3 is 3x. So again, what I want to do now is plug in 4 and plug in 2, and I want to subtract them, okay? Well, make sure you're using parentheses here. So again, I'm going to plug 4 in. That'll be 1/3 of 4 cubed plus 3 times 4. That whole thing should be in a parentheses. And then I'm also going to have 1/3 of 2 cubed plus 3 times 2. Okay? And I like to solve these things separately and then combine them at the end so I don't make a parenthesis mistake. Okay? So this one's obviously going to be a little bit more difficult because of that 1/3 in there, but we can still get the correct answer. So let's solve. 4 cubed, I know, is 4 times 4 times 4, which is 64. So I'm going to get 64 over 3 plus 12. Working over here, 2 cubed is 8, so I'm going to have 8 over 3 plus 6. I'm just going to combine things here. 64 plus 12 times 3 is 36. 64 plus 36 gives me 100. So I've got 100 thirds minus, so I got to do times 3 again. 18 plus 8 is 26. And 100 thirds minus 26 thirds. Well, 100 minus 20 is 80. Minus another 6 would be 74 thirds. And so that would be my final answer. Again, I can go back and check this thing. I'm going to do it the quick way, math 9. Come on. Let's try that again. Math 9. Okay. Integral from 2 to 4. X squared plus 3. And then put in my dx. I get that answer. And I can just change that to a fraction to make sure it's right. And I see 74 thirds. Again, you got to be careful with your parentheses because a lot of people make mistakes, not conceptually here, but they make just simple algebra 1 mistakes by not grouping the right terms and doing order of operations correctly. Okay. Let's try another one. So I'm doing the integral from 0 to pi of sine x dx. If I think about my graph of sine, I know sine starts at 0, goes up to 1, and comes back down here. I know out here is 2 pi, so I know here is pi, right? I'm finding this area in here. So let's think about the antiderivative of sine. Well, again, this is one we have to have memorized. You have to know that the antiderivative of sine is negative cosine x. Because the derivative of sine is positive cosine, the antiderivative of sine is negative cosine. So I'm going to get to my bracket, negative cosine x. I'm evaluating this term from 0 to pi. So what I have to do here is negative cosine of pi. And I always like to put the first one in parentheses, even if I don't totally need it, and then put the second one in parentheses. Again, we can think back to our unit circle. I know pi is over here. That's at the point negative 1, 0. I know cosine is x. So I know cosine of pi equals negative 1. So what I have here is negative 1. Lots of negatives in this problem, so just something to keep an eye on. I know cosine of 0. 0 is right here. I know cosine of 0 is 1. But again, I have negative cosine of 0, so it gives me negative 1. All right, so negative 1, I know becomes 1. Again, it's going to be 1 minus negative 1, which is going to be 1 plus 1, which equals 2. And again, I can confirm that on my calculator. Let's see, where's my arrow? There it is. Integral 0 to pi sine x dx It confirms my answer at 2. Now, I'll show you one more. One more example. Integral from 1 to 9 of 5 over root x dx. Okay. Now, before I get to my antiderivative here, this isn't an ax to the m form. It's also not a derivative that I immediately recognize. So I'm going to want to take a second to rewrite this. So I'm not going to put my brackets yet. I'm going to rewrite it with the integral S curve and do this. Again, I know square root means half power. It's also in the denominator, so I need to move it up to the numerator. So that makes it a negative half. And again, now I'm going to bump and divide. So I'm going to bump my power up by 1. Negative half plus 1 is positive half. I'm going to divide by half. But again, anytime I divide by a fraction, I multiply by the reciprocal. So instead of doing 5 divided by a half, I'm going to do 5 times 2. 5 times 2 is 10. Now, since we're evaluating, I don't want to have negative powers. I also want to change fractional powers into the types of roots they are. So I'm going to do one more rewrite here. Which means that half power into a square root. Okay. Plugging in then, I get 10 root 9 minus 10 root 1. Okay, well, root 9 I know is 3. So I have 10 times 3 minus root 1 is 1 times 10 times 1. That's going to give me 30 minus 10 for a final answer of 20. Again, let's check. Where's my mouse? Let's check this one on the calculator. I'll do math 9, integral 1 to 9. I'll put in my fraction. 5 on top. And root x on the bottom. And you see it spits out 20. So that's how we perform definite integrals. That's all I've got for you guys today. I'll see you on Monday, and we'll get some practice solving these bad boys. Talk to you guys later. 2 chains, bye.